Connor, thank you for taking the time here today. Join the show. How are you doing today?
No worries, pretty good. We were just talking about weather before, and it's actually sunny here for once, so I'm really happy about that. Though I am getting
Yeah.
grounded.
Well, I mean, it's like end of February, so it's like it's bound to start turning soon. That's my thought. And
Yeah,
it's sunny here too in Belgium, which is like a miracle. So, yeah, we picked a good day.
yeah.
Um, I wanted to start because I spoke with you before, probably it was about a little over a year now, about a paper that you did. I wrote an article about it, and so I want to talk about nanomaterials. I want to talk about sustainable chemistry and space, sustainable space exploration, all of these things. But I wanted to start with maybe you could give us the definition of what it is that you do, because to me it feels like there's like engineering, there's material science, there's chemistry, all of these things kind of floating around. So if you had to label yourself, the work that you do, the research that you're interested in, what would you call it?
To be honest, I wouldn't even know. I don't even consider myself a scientist. I think I'm more like an observer of kind of the world, kind of, because a lot of our ideas just comes from just looking around and then kind of like seeing something in the news or seeing something on telly. Like we had a paper out on like loads of stuff about seaweed, but I originally saw it on MasterChef during lockdown. So I mean, it's just like I just had an idea. It's just like, oh, that's kind of interesting. I mean, I would just say generally just a material scientist, I guess, because material science is such a broad area. It does encompass kind of entirely STEM, that it's kind of like it is engineering, it has a little bit of science, it has some of like, computer science associated with it as well. So I mean, generally I would just think that I'm just a material scientist. But yeah, we do a lot of different kind of things, a lot of different applications associated with our work. But mainly it is just around nanomaterials or, sustainable polymers and stuff like that.
Okay, so we'll get into maybe some of those definitions of what those things are in a second, but I'm material science was something that, yeah, like I had never really heard of. I studied biology, so I did physics, I did chemistry, I did biology courses and stuff like that. Engineering to me was always kind of like, okay, that's a very applied thing. They're doing kind of math and structural stuff. But when I started doing science writing, science journalism, I found myself writing a lot about chemistry and material science, which chemistry I almost failed that course many times in
I
university.
look
So
at you in awe because I'm dyslexic, so I could not do biology. The names were too long. All I remember is the kingdom, phylum, class, order, family, genus, species. That's the only thing I
yeah.
remember from biology. I was terrible at it.
Well, I think it's because biology is a lot of memorization. Like it's a lot of reading and just memorizing. Okay, well, this thing does this,
Yeah.
like this part of the cell does this thing, or yeah, the classification of animals and stuff. Whereas the other sciences, there is a bit of like, if you can solve an equation, then you can kind of do it all sort of thing, right? Whereas that was like, I would consider myself dyslexic with math. I would do these long algebra problems, and at the end I'd be like, I don't know where I made this mistake, but somewhere I, flipped a 6 for a 9 or something, something like this.
Yeah.
So biology was always me because I was like, I can read it, I can memorize it, I can understand it. That's it. There we go. But I was surprised to find myself covering sort of material science and chemistry and this kind of thing. But it really feels like it's, I don't know, maybe you wouldn't say like an emerging field because it's kind of been around for a while, but we are at a stage, it feels like, with a lot of technology that since we've unlocked some things about some of these materials, we've been able to make a lot of technological advances,
Yeah.
whether it's batteries, different minerals that we're using. I mean, even smartphones, like the touch screens, like all of these things are being unlocked, but it's because of the materials, right?
Yeah.
So that to me is kind of this interesting thing. And so that's what I view material science as, like looking at the things that we have available to build with or to use, and then how do we use those things in new and interesting ways. Is that
Yeah, I mean, like, I can't agree more that it's just kind of like just how technology progresses. Because I mean, if you just look at like the airplanes, it was like they invented the airplane, then about 20, 30 years later, there was airplanes in war, and then they were commercialized that you could fly in them. And then 20, 30 years later, we were then trying to go up into space. Like, it's just, I think just kind of just the way that we've rapidly progressed as a society is just absolutely insane. because I mean, like we're not that old, but like when we were kids, you didn't have cell phone. Like that was just like
Yeah.
science fiction. But now what you can do with cell phones is just absolutely ridiculous. Like it's amazing. But yeah, no, I think kind of material science is just, I think like what I always learned when I was kind of in college is like to kind of be successful in material science is that you could never be good at just one thing. You need to understand chemistry, you need to understand physics, biology, maths, so just all of it kind of encompassed together because it's just such a broad discipline, it's such a broad field, and just kind of just the applications of the materials. It's just there's just a huge plethora of them. I mean, what just even kind of graphene, I suppose, the kind of quintessential nanomaterial that a lot of people know is that like that there's energy storage, energy harvesting, so making new batteries, getting clean energy or hydrogen gas, should I say, and then kind of just even all the way to like really, really simple things like just taking graphene, putting into a plastic and making it stronger. So it's just like a wide range of applications going from something super simple to something very, very complex that's out there. And I think that's what's kind of like really interests people, I suppose, about the field. But no, you are right that it's a young field. I mean, I think a lot of people that do nanotechnology and material science would say that it's still in its infancy. Because I mean, it probably kickstarted maybe 20 years ago or so, maybe 25 years ago, because the nanotubes were only discovered in the early 90s in Japan. And then graphene was only then, the early noughties. So I think about like 2005, 2006. So I mean, it's really not that long ago that we didn't have a lot of these materials around, and we're still kind of learning so much about them already just today. It's just simply kind of taking two graphene nanosheets, people discover that if you just kind of just have them kind of slightly aligned, weird on top of each other, all of a sudden it becomes a superconductor. So it's just that's something that we didn't know 2 years ago, and it's something that people just found through serendipity, just by chance. And now it's like open up this whole new field of kind of just can we make superconductors out of graphene now? So it's just a really, really interesting field that's just kind of just sprawling across all of STEM.
Yeah. Yeah, to give it that time frame of like late 90s and then, early 2000s, that's way younger than I than I would have guessed. But
Yeah,
it makes sense. It kind of lines up, right? Like that's when you start to see all of these cool things. So one more thing before we get into, we'll use graphene, I think, as an example. We can go into of a nanomaterial, but the you mentioned you consider yourself an observer of these of the world, and I mean, to me that is science, right? Like you're looking at things, you're trying to figure things out or trying to see what's useful. But with the material science and the way that the way that you described that there really kind of jumped out to me because we have all these materials that we already use, but then you're looking at them and trying to say, well, is there another way to use this, or what happens if we put that material in this condition or something like that? So it really feels like, rather than sort of this, I mean, I guess it's probably still hypothesis driven in a way, but
yeah,
it's kind of this, I don't know, I'm reluctant to use the term mad science or alchemy, kind of thing, but it really kind of is, where it's like, well, here's a material, let's put extreme heat on it, or maybe it'll do something weird if we add this to it. And
yeah.
there's something really kind of creative and interesting to me about that.
I think there's just probably what a lot of people think about science is that like a lot of people kind of go into the lab and they're inventing something like completely new, and that certainly is the case with some stuff. But I mean, a lot of it is like iterations, but they're kind of like large steps in the iterations of kind of the devices. Like I mean, unlike the transistors in our computers and stuff, is that we're kind of using silicon and all these kind of materials that everyone knows, and then kind of then using nanomaterials. It's like a huge jump into this kind of new performance in these materials and or in kind of computing, and it's just it doesn't seem like kind of like a big deal, but it's just kind of like when you kind of do it, everyone all of a sudden kind of goes like, why didn't we kind of think of that before or something like that? I think it's just kind of one of those things. Yeah, it's like a lot of science isn't kind of just like all of a sudden just someone just going, I'm going to go out there and I'm just going to invent a new rocket or something. It's just,
Yeah.
it is a lot of kind of iterary, kind of clever thinking of maybe how to redesign something that we already have. Because I mean, it also kind of facilitates these technologies kind of helping us, in the short term, is that, if you take something that we're already kind of commercializing. You just slightly improve it with, something nano. It's just like its chances of meeting or getting to the market or meeting those standards of commercialization are much, much narrower. It's so like it's so much closer. And I think that's kind of one of the big things that people always say. It's like, oh, graphene's the wonder material. Like, when am I going to see it? I hear so much about it. And so there are little things of graphene kind of trickling out there. And I think it's just people don't appreciate the fact that it's like it doesn't have to be like this big boom of all of a sudden graphene technology and everything's changed. It's these small things. Like I know that there's kind of capacitor systems out there in China that use graphene batteries and battery electrodes and all this kind of stuff. So it's like it's out there, it's being used. They're integrating graphene into plastics, into the hulls of ships, into the hulls of cars, tennis rackets, helmets, and stuff. So it's like it's slowly getting out there, but I suppose it's just people expect like it's going to be something crazy, like, oh, okay, we've got the graphene bot now, like a mechanical robot that's out there, and everyone's like, yeah, that's what we were expecting. But it's just like, no, these kind of things they trickle along. I suppose it kind of maybe takes a little bit of the wonderment out of it or something, but it's just, yeah, it's small little iterations, and then when we look back in time, we go like, wow, that was something that was kind of very important. So I think it's just we have to like remember that it's just like if we look back in hindsight of everything that we've kind of accomplished so far, it's absolutely crazy. Because I mean, 10 years ago or whatever, 15 years ago, we only discovered graphene, but it's already now being commercialized. And that's like huge. Like that's so quick. I mean, I don't think you get FDA approval for a drug that you discovered 15 years ago. Like, I mean, it'd probably take 30 years, 40 years or something like that. It would take forever.
Yeah.
So, I mean, yeah, it's just these things are kind of small. And I mean, yeah, as I said, I suppose like for me, thinking that like kind of an observer, I suppose kind of the things that I look at to try and change, they're probably like a little bit more unusual. And I suppose that's what kind of makes them, I suppose, a little bit more eye-catching, I guess. And, kind of these Martian materials that, trying to take something that's kind of already on Mars and trying to use it to our advantage. I suppose that's kind of maybe unique take on it, whereas we're more focused on how do we get everything over there and get the people over there. It's like, well, what happens when we get there? Can we not use anything that's around us? And I suppose that was kind of our take on it. That it's just surely there's something advantageous up there. I mean, then why go there? It's just a rock. I mean, it's cool to say that we would be like a two species planet and all that kind of stuff, and kind of a kudos to us, like a pat on the back that we've colonized. But it's just like we got to do something while we're up there. So
Yeah, yeah. Well, that's yeah, and there's lots of questions that we could do with space, like the different mining asteroids and like who knows what kind of materials are out
yeah.
there, that kind of thing. But let's we've kind of teased this now a little bit, and thrown this term around graphene and nanomaterials and stuff. So let's break that down first because I was shocked when we first chatted about where graphene comes from and just this idea of nanomaterial. So maybe you could define nanomaterial and use the example of graphene, where it comes from, how it's made, and what makes it a nanomaterial, and why nanomaterials are so interesting.
Well, actually, there is actually like a definition for nanomaterials, so it isn't kind of like a wishy-washy thing that we kind of just go like, oh, that one's a nanomaterial, and I don't like this one, so I'm not going to say it's a nanomaterial.
Okay.
So it's just that one of the dimensions of a material needs to be less than 100 nanometers, and
All right.
that's essentially it. So it's just you imagine that you take like a block, and if you just decrease maybe its height down to being 1 nanometer or less than 100 nanometers, then it would then technically be a nanomaterial. And that's essentially what graphene is. Graphene is just a sheet, a very,
Right.
very thin sheet of atoms. But yeah, it comes from graphite. So graphite is like a deck of cards when you look at it under a microscope, but each one of those individual playing cards is a sheet of graphene. And then we kind of then use chemistry and stuff to then break apart this deck of cards into the individualized sheets. And then we can then kind of play around with them and use them. And generally, we do this in kind of liquids. An issue when graphene was discovered is that people literally got tape, put it on top of graphite, and then started to just peel off the layers. And that
And
was an issue.
graphite is just like pencil lead,
Yeah, it's
right?
just pencil lead. Yeah. So it's just essentially your pencil lead. And we've shown as well, like in a paper that we did a couple of months ago, is that you can literally take pencil lead. and you can turn it into graphene, and really, really good graphene that's similar to the stuff that you make from, going to a commercial supplier, specifically buying graphite that's been milled up and everything to then use in labs. Is that you can take any old graphite and then turn it into this kind of wondrous material.
Right. So you got, so to make your nanomaterial, it's got to be really thin, and it's usually these thin sheets. That's how we think of it, right? Is like
Yeah,
these
so we
thin
have
sheets
these
of.
nanosheets, and then also you can have the kind of tubular shapes. Is that, you kind of decrease another dimension, and you essentially make this elongated array of atoms. Is one of kind of the other forms of graphene as well. So you can take a graphene sheet and essentially have it rolled up to form a tube, and that's the carbon nanotube. A carbon
Hmm.
nanotube is just a graphene sheet just rolled up, or a graphene sheet is a debundled or kind of a unscrolled nanotube material. So they're just all what we'd call in chemistry like allotropes of carbon. It's just the different forms in which carbon kind of form together. But graphene isn't kind of the only nanomaterial out there, or the only atom that kind of or element that forms nanomaterials. We have a whole zoo of them. So we have boron nitride, which is boron and nitrogen atoms similar to graphene that just kind of just sits in a sheet, and it's an electrical insulator. And then you have something called molybdenum disulfide, which is just molybdenum and sulfur atoms again in this kind of just planar sheet form. And then that's a semiconductor. And right there, you have kind of the basis of kind of your basic computing. Is you have graphene, a conductor, you have a semiconductor, and then you have an insulator. And then that's where you can go and kind of start making electronic devices. Then
So then, when you break, you got graphite, which is boring pencil lead. You put it into this graphene form, this really thin thing, and it gets like new properties or enhanced properties. How would you describe that?
we
And
we would say that it kind of like, yeah, that it like enhances it, it optimizes the properties, and which is why it kind of why nanomaterials are so exciting. Is that if you look at graphite, we all know from kind of with a pencil, you're writing and it's very brittle. You're constantly having to sharpen it, so it's not very, very strong. And then also, then if you take graphite, it's not a very, it conducts electricity, but it's not an amazing conductor of electricity. But when you then optimize it by breaking it apart into the graphene nanosheets. Graphene is one of the strongest materials that we know, because it's based on trying to break molecular bonds in the actual sheet, rather than with graphite. It's all these sheets sitting on top of each other. So when you start to then try and pull it apart, it's just the sheets coming apart rather than actually pulling the actual graphene sheets. And then also as well, graphene is an amazing conductor of electricity and heat, because it's just this single sheet, so the electrons can just zoom across the surface, rather than in graphite, it's all this muddled amorphous structure. So all the sheets are all crumpled up and they're all smushed together. So to go from A to B across the graphite, it's going to go like up and down, and oh, I have to go backwards and forwards and everything. So yeah, it's essentially it's just optimizing the properties when you, what we would say, exfoliate these kind of layered materials down to their kind of nano form. And it's the same with, molybdenum disulfide as well. Is that when you kind of start to strip away its layers and get down to the single layers, you actually are able to kind of tune the band gap of the material as well, and tune its properties to make it more advantageous for electronics. Because in the bulk as well, molybdenum disulfide, it isn't used for anything in electronics. It's actually just used for a lubricant most of the time. It's actually a very, very good mechanical or solid state lubricant. So you literally just get the rock and you kind of rub it around the joint, and all the layers come off, and they just form this kind of just slippy layer that you can then kind of just put two metals together, and they'll be able to form some type of actuation where you kind of have the mechanical gears going. So it's essentially you're just discovering all these amazing properties from these materials by just kind of turning them into nano. And it's the same with, looping around to our Mars study as well. Is that we just took kind of boring rocks that people more or less assumed had, not very interesting properties. And when we exfoliated them down to then kind of their nano form, or into these kind of nanorods, is that we found that they actually turned into semiconducting materials, and they have these very interesting properties, and they could, have the clean energy harvesting, and, we could use them to kind of reinforce polymers. So it's just like, this is what's kind of very exciting about nanoscience, is that it's like that unknown. It does seem like a little bit, I suppose, when I say it, kind of repetitive, because you can just keep on going. well, let's just get that material and try and see if we can turn it into a nano sheet or a nanotube, and let's get that one and let's get that one. But the thing is that it is cutting edge science because we simply don't know what's going to happen to these materials when they go down to the nanoscale, and that's when all those kind of crazy properties come out.
Okay. So that was kind of what one of the other questions I had was, can you sort of predict what material, when broken down to a nano level, will have interesting properties? But before I get there, it's like, do all the nanomaterials, is it all just about sort of stripping away the sort of resistance is maybe the wrong word, or the clutter, right? And so when you get down to like those sort of atom level, thinness, you just, like you said, electrons can move much faster. It's stronger because you're actually trying to break the bonds and not just this brittle layer of stuff. So is it
Yeah.
really just like, is that sort of the core of what makes nanomaterials, or is there other sort of, sometimes I think about it, I could be way off, that it's like, when you get down to the quantum level of things, like there's this weirdness that we don't
But
understand. So is
that
there something
that
that we don't?
It's yeah, it's a lot of the quantum effects that start to kind of come into play when you start to go down to those very, very small dimensions, and you start to have all these kind of funky effects that occur. I won't go into because I don't want to go into like a huge amount of kind of physicsy stuff. But I mean, like, yeah, that a lot of it is to do the going down to these kind of quantum levels when you start essentially you almost have like a macroscopic material that's then being confined down into these kind of quantum realms, and it's that kind of combination where you kind of get these really, really interesting properties. But to go to your point of kind of being like, oh, can we kind of predict what a material might do? Is that not all materials can kind of be broken down into some type of, I suppose, nanomaterial. Like I mean, for kind of bricks and mortar and things like that, like they won't necessarily form some type of structure like graphene, like a sheet, or that they won't form these kind of nice tubular shapes or anything, nothing kind of
Okay.
uniform. So it has to kind of really depend on kind of the actual physical structure and the lattice makeup of the material, to use kind of a physicsy word, like how the atoms kind of arrange together, for us to be able to kind of go like you can see physically where you could kind of strip down the materials. Because I mean, going back to graphite, is that you can see the layers in
Right.
graphite. So you can kind of see, okay, so this is what's going to happen when we try and use these exfoliation regimes. It's going to peel off these layers. We're going to get some thick layers. And if we keep on this peeling process, eventually we're going to get down to a single layer. And then if we keep going, we're going to then start to tear up these kind of smaller layers, and, being able to kind of control size and stuff. But yeah, it seems like for some materials, it seems like people are very good at kind of predicting the properties. I suppose that there's a lot of and like for molybdenum disulfide, it's kind of in a family of materials called the TMDs. So it's basically just like removing molybdenum and then kind of replacing with maybe like tungsten or something, or removing sulfur and then replacing with nitrogen or something. You're kind of removing atoms. So they all have like roughly the same shape. And because you know so well about one material, you can kind of through analogy be able to use computations to predict the properties of other materials. But
Hmm.
then if you kind of have materials that you don't know a lot about, when people do the computational stuff, this is where you can kind of get this kind of mismatch between experiments and then act or experimenting and theory essentially. And this is
Right.
what we kind of saw with a lot of our materials, is that we worked with physical rocks in another study called phyllosilicates, but they're like micas essentially, like these kind of generic flaky little rocks, and they're commonly believed to be just like clay or all these other types of kind of flaky materials, is that they're insulating, they're not very strong, and essentially they're boring, and they're not interesting at all. And people have kind of done some computational studies about stripping them down to their single layers, and they go, oh, they're even more boring. Nothing happens, nothing changes with the properties. But there was this one study where they just by accident decided to strip them down and try and look at their electronic properties, and what they found out is that these kind of mica materials and these phyllosilicates, they have this huge variability in their electronic properties that no other nanomaterial has. But
Hmm.
everyone just wanted to ignore them because they were just like, no, the computational stuff says that they're crap. So it's just it was just one of the things that's like, oh, maybe they did something wrong in their study and all this kind of stuff. And I was just like, no, these are good researchers. They clearly are onto something. So what we did is that we took a bunch of them, we exfoliated them all down. We saw exactly what the other people saw. That they had these massive tunable electronic properties, and we were able to kind of figure out through kind of modeling and stuff why people, when they were initially looking at them computationally, why they were seeing the wrong data. And this is where you can kind of see this kind of mismatch with the theory and the experiment, is that you really need the experiment to back up the theory. And sometimes you kind of have people that just go, theory says no, so let's all just ignore it. So it's just like, yeah, it is actually surprisingly difficult to predict the properties of the materials. I was definitely, before we did the study, under the opinion of, well, like the computational people, like they're actual nerds, like they're proper nerds, so they definitely probably know what they're talking about more so than me, who doesn't even think I'm a proper scientist. So I was just like, I'm just going to believe what they say. But it's just like, no, like these people, like they did experiments, they can't be wrong. All the experiments look right. It's been peer reviewed,
Hmm.
it went into a good journal, so it's like they have to be onto something. And yeah, when we looked into it, it's just like it was the first case that I'd actually seen, like, oh, maybe the nerds don't always know what's going on
Yeah.
all the time. But yeah, it was like
Yeah. Yeah.
it it led into then what we did with the Mars stuff, is that essentially people thought similarly, oh, gypsum, it's not a very exciting material. We've investigated it computationally, and it doesn't seem to have exciting properties. But again,
Yeah. That's interesting. And it, I, yeah, it's like the modeling, the theory, like when it works in the example that you gave before, I can't remember, with tungsten and like flipping those things out, then it makes sense, right? That it's like, okay, we know something about this material, the atoms that were the elements that we're putting in there are similar, so it all tracks, right? But then
yeah,
there's still this sort of mystery level where it's like it says no, but if you test it, you never know. There might actually be something in there, and that's
yeah,
where that mystery level is still, that to me is so fascinating, because not only is like nanomaterials itself this brand new thing, but then you get down to this, well, why this one? All the nanomaterials, like we get this idea, sheets, tubes, it's gonna work, it's gonna be this interesting thing, but then we have this obscure material that shouldn't work based on all of those things that we
you
just discussed, but
you're
it
but
does.
you're actually describing the history of nanomaterials, because the thing is that people said that graphene couldn't exist. The
Ah.
computational people said that graphene physically, thermodynamically, everything, looking at backwards, forwards, it could never exist. If you made a single sheet of or of graphene, it would instantaneously crumble in on itself, like that it should be
Ah.
completely unstable. And it wasn't until the lads in Manchester isolated it that everyone just went, oh yeah, I guess they were wrong. So it is kind of one of those things that it's just like those kind of like computational assumptions actually nearly like stunted the nanoscience revolution, I guess, or kind of the field. Is that if
Right.
people believe that it's just like, okay, maybe the computation people are right, let's not bother explaining graphene at all, then it's just like we wouldn't be where we are today.
Right. So it's like, yeah, don't always trust the modeling nerds. But do we do we do we know then where the flaw in the model was?
I think it's just
Like,
always with kind of modeling, is that it's just like it is only as good as the experimental data. And I think it's just like if it
right.
doesn't match the experimental data, then you need to adjust the modeling if the experimental data if there's no obvious flaws with that. So it's just like I think it was just one of those things that I think the data wasn't there. So
Mm,
there was just, I guess, the need for modifying the data was just, I don't know, I guess it kind of seemed like maybe just it wasn't, there wasn't any points.
right, right. Yeah, I mean, it's kind of a weird, like really sort of probably like technical question, but it just seems like one of those things is like, yeah, if all the theory, again, it kind of makes me think of that quantum stuff, right? Where it's like all the equations say one thing, but when you get down to this thinness, this realm, it's like the rules change,
It actually
and
isn't that, it wasn't that actually difficult or even kind of technical. All it had to do was the fact that the theory stuff didn't compensate for the size of the materials. That was it.
mm,
Is that with the materials, their electronic properties were actually not only dependent on the number of layers they have, but also the size. So when they started to get really, really small, they started to look like insulators again. So they started to look like they're bulk materials. And all the computational models can only assume small nanosheets. So that's where we saw the discrepancy, is that because they assumed that they were always, or they could only model them being small, that they always had these effects that made the band gaps appear large. Whereas because we could do it experimentally, you could control the size, we saw that as you changed the size, the actual aerial size of nanosheets, that also changed the band gap size. And
Interesting.
that was it. It was like it turned out to kind of just be something very simple. But it's just the fact that like just no one looked at it, and it can always turn out to be something just as simple as that. It was just literally just they just weren't thinking about the actual size. They were looking at the layers, but they just weren't looking at the actual size you could actually get. And that's why the initial people, they got all these fantastical results, because when they were making their nanosheets, they were massive, they're absolutely huge, and they were able to get them so thin, and that's why they were able to get these fantastic electronic properties. But yeah, it's like when other people did the modeling, they were like, no, we don't see this at all. And it's like, you need to think about their nanosheets were huge. Yours, you're assuming very small. So that was literally it. It was as
Wow.
simple as that.
This is like, okay, so a bit of an aside, but this is something that I talk about a lot, is like, this need for the argument or the case for basic research, right? And like this feels like one of those things where it's like if someone doesn't just try it or like ask the question, right? You could do all the models could say all this stuff, and so you might, but if someone until someone just actually does it, you don't know. And I think that that's, I'm going to make a point again here for like, this is why you do basic research, right? This is why you read somebody's paper and you say, oh, they did that. Interesting. What if we try it this way or something like that? And I feel like
Yeah.
there's so many, you got the politicians and the public that are like, well, why are we funding all this stuff, right? So there's a lack of understanding there. But then even just within the science community, people get so siloed, right? They get so focused on their one thing that they don't sort of look to other fields and see how, serendipitous discoveries or cross pollination of knowledge, all that kind of stuff goes on. I just, maybe you have a thought on this, but this is something that I think about a lot as like science communication, because we often scientists think about, wow, we got to communicate to the public and we got to justify what we do. So this is a good justification for that. But there's also this interdisciplinary communication that I feel is lacking. And you probably would lose some of these interesting discoveries, or someone's going to take what you found and do something interesting with it. So,
I think a lot of it is just probably the kind of the mentality in academia, that it's just, I think when people kind of feel that someone's like has a question about their work, I think it's always kind of like interpreted as being kind of negative, or that you kind of need
mm,
to feel like defensive and I need to kind of justify my work. And I think, yeah, a lot of that kind of conversational aspect of academia kind of goes, it's just kind of just gone away. I'm not sure if it was ever there. I think it might have to do with just kind of just the modes in which we publish. Is that, you have anonymous reviewers, and they can sometimes be very critical or negative, and sometimes rightfully so, sometimes just overly critical for, I don't know, their competitor or something. And I think it's just, I don't know, it's just a negative mentality, because I mean, what I kind of like think of things is that like people always go like, oh, like an industry person or something, like, who's your biggest competitor? And it's like, I don't see research like that, and I don't think people should. Like, I'm not trying to compete against someone to do something. It's just like everyone is potentially collaborators. It's just like if there's someone else working on something just like I am, they're working the same thing. I'd rather reach out to them and be like, what are you doing? We're doing this. And it's just like, we're getting this wrong. And I see you're getting this wrong. Like we could work together on this. Like I see like there's more benefit to that than kind of just being like, oh, I don't like you because you do the same thing as me. So you're a
mm-hmm.
competitor and I'm never going to talk to you. And it's just like, well, that person could be an expert expert in the field. And it's just like you're missing on this, yeah, as you said, cross pollination, this knowledge, this kind of expansion. That's just like, this is how we'll get to this like next technological era. It's just like we need to stop being so damn competitive. It's just,
Yeah, well, in a way though, I understand, that there's like competition for grants, right? Like there's only so
yeah,
much grant money to
yeah.
go around. But I wonder, do you feel that maybe in this area, do you find that it's really collaborative? Because I could also see, proprietary, commercialization of some of these things coming in too, where people then want to be more guarded about what they're doing.
I think I think with regards to kind of like thinking about commercialization, it's definitely always kind of like the universities. The universities are always very aware of kind of what might be like sexy IP and stuff. So there, I think the
Hmm.
universities are, like there are definitely kind of researchers that are very forward facing with regards to kind of industry. Like, I mean, I consider myself that as like, I definitely would love to have research that culminates in something that's useful. But I mean, like, odds are, and like, I'm not going to like lie to myself is that like most research and probably most of my research may not come to fruition, but it's just like, if you have that ability to kind of have research that will influence policy or be able to kind of influence others to maybe go over the edge, I mean, I think that's just as satisfying. But yeah, it's just, I think, yeah, a lot of the gear towards kind of protecting IP can come from, just the setups within countries and the setups within universities. Like I know in the States is that a lot of the universities is that when they look at funding, it's what's the dollar value that you get back from the funding, which is always a
Right.
huge thing. I know in the States is that we're going to pay for you to do this research, but how are we going to make money back on this investment? Whereas in Europe, it's a little bit more lax, is that there is, like, I wouldn't say exactly kind of fundamental research, but they are more willing to understand that grassroots research needs to occur in order for that to kind of reach momentum to get to commercialization. There is still that want for commercialization, but I think the push is getting there, but I think it's not as extreme in kind of other countries. But yeah, the only analogy they can kind of think of is obviously the powerhouse that is the United States. And yeah, I know that a lot of the research and a lot of the professors are under stress or duress of being like, I need to come up with something that's going to make money. And I think that can be kind of that can lead to that kind of competitive inward thinking of just being like, I can't tell anyone about this. I need to think
Hmm.
about myself and all this kind of stuff. And yeah, as you said, people want to get the grant money to be able to do this. And I think unfortunately in those situations you will then have to be selfish, I guess.
Yeah. Yeah, it just it feels a little it feels like sometimes especially like from even the funding, the people providing the funding, which I guess goes up to government and politicians that maybe don't understand that like without that foundation of just basic research coming up with, ideas or bits of information, bits of knowledge that then that's what slowly builds towards the breakthrough
Yeah.
technology. But and you see I see it a lot in doing science journalism, right? Is because it's like even a lot of websites or magazines that you write for, they want you to report on what this is going to mean.
Yeah.
What the tech. So you have so many times this sentence in an article that's like this thing might one day lead to this treatment, or
Yeah.
like somebody studying grasshoppers was an example that came up in another podcast where it's like they're studying the way grasshoppers jump or something like this. And it's like, oh, this might make a robot one day. Like we could make jumping robots or something. It's like, that's
Yeah.
never going to happen. Like, it's like,
Yeah.
it's not useful, but like everybody's trained to have this economic, sort of commercial justification for what it is they do rather
Yeah.
than, well, I'm creating knowledge and we don't know where that's going to be useful. But I think you can philosophically make the case that more knowledge is
Yeah.
itself valuable.
It's that saying that like literally everyone repeats. I think what was it, Einstein or something, that we stand on the shoulders of giants. That it's just,
Yeah,
it's just it's this little information that we need this accumulation of information before we get this big jump. And I mean, I think that's the case in pretty much like all industries. So yeah, I think it is just. I would say it's kind of like disappointing, but yeah, I think that's where kind of the pressure does kind of come on, that it's just, what value would this kind of come? And I can understand kind of the public's feeling of it as well, is that, when they do read an article, they do want to know like what's the outcome. I suppose it's like it has to be almost like a story that it's the beginning, the middle, and what's the end, and the end is going to
yeah,
be this proposed technology. So, and it's public funding as well, so I can kind of understand people as well wanting to know
yeah.
what's going to come of this research that they hear so highly of. But yeah,
But I
it
think
is
that that's
tough. It's a tough
actually,
balancing act.
yeah. I think from the public standpoint, I think that might be a bit of a myth that they care because because the one thing that's like, and again, this came up in another podcast I did. it's like the biggest topics, and I see this again as a science journalist, the some of the most popular topics that the public, let's, air quotes, this general public are fascinated with is like astrophysics, which impacts their life not at all. But an article that's about like a new theory of time will say that like maybe time doesn't exist, right? That's not going to impact your life in any way. But these are
Yeah.
the ones that like people love, right? And it's like, I don't know. Can't explain it. Can't
I
explain
suppose
it,
it's
but
like the
people are just fascinated by that.
pop culture. It's kind of like, we have kind of trickled through this kind of science fiction and everything. It's kind of trickled into society. And I think it's just kind of just like, I suppose the exciting yeah, the excitement around kind of like the unknown implications of these kind of things. Because I myself as well, when you kind of see all these things like, oh, time dilations around the corner, and all these
Yeah,
kind
yeah.
of mad things, is that, yeah, it's just kind of like it's that what ifs that kind of come up that I think is that are kind of very exciting. And I suppose that's like the thing with like space travel as well, is that it's just like yeah, it's not the idea. I think that people are always like, oh, like, oh, the technology to get there. It's to get there, and then like, what happened? Like, what will it be like there? And I think that's what kind of really excites people,
Yeah.
with those kind of things. That's like that. I suppose, like, it sounds ridiculous, but they almost do feel like things that could be more effective on your life or could have large effects on your life, even though, as we
Yeah,
said,
yeah.
they're going to have absolutely nothing. But it's just like, well, what happens if I'm just walking down the road to get donuts and then all of a sudden I step into a wormhole or something? I
Yeah.
think it's just like that fantasy of just being like, oh no, I'm falling through time, but I read about this in this article by Bradley. Like,
Yeah, yeah, yeah. Yeah, I think it's like it's interesting because it's like we have this, there's this evidence that people are just fascinated by the unknown, and that, and like that's, I think you can go through history, right? Like this is why people have explored all the different, there's something about humans being, but yet in science and science community we kind of go away from that and be like, no, we have to justify dollars and cents as to why it is. It's
yeah,
like, yeah, maybe sometimes just lean into the like the wonder of it all, right? Because
yeah,
I think that's why most people who are in science get into science, and then that can also get kind of beaten out of you a little bit. But let's go to the space stuff because I want to cover this before we before we run out of time. Because this was, yeah, really interesting to me because it blends kind of two ideas. There's the space exploration, the space travel, which we just touched on, interesting just for the sake of being interesting. Humans were these explorers, but there's this sustainability angle to it, which you have kind of a philosophy in your work. If I'll paraphrase what I'm thinking, and then you can tell me if I'm correct or not. But when it comes to, let's say, making nanomaterials and using nanomaterials, can we making them in a way that's not like harmful to the environment is in itself valuable, but then being able to make the nanomaterials without like a lot of complex, machinery or solvents or, chemicals, these kind of things means that hypothetically someone that's on Mars with limited, resources, because you can only bring so much in your spaceship, uh, might be able to fashion some of these very useful materials using very little. I've kind of thrown it all out there. Maybe you can kind of streamline that a little bit, but I love the sustainability angle just for the sake of the planet. And then also, it will make things easier when you're in space.
yeah. I mean, the thing is that like people are gonna like laugh, but it's just like I truly feel that like the type of nanoscience that like my group does and kind of some of the people I collaborate with, like anyone can do it. Like literally, I don't think you need any background. You could go into the lab, and you can start making like graphene like immediately because it's just that it's is such a simple process that we use. So it's called liquid exfoliation, and it's a process that was pioneered like actually here in Ireland in Trinity College by Jonathan Coleman, who I did my PhD with. So that's why I do it this way. Is that it's such intrinsically simple process that it's just you take essentially the bulk material, you put it into a liquid, and just apply some type of energy to it. So generally it'd be like sound, and it's literally just the high pitched sound that goes into the liquid, and it kind of just bursts. bursts into the liquid and kind of breaks apart the material. Or you can use these little sonic bats that do the exact same thing, just at a lower frequency. And they're actually things that are used in jewelers to clean jewelry. And that you'd actually see around. And I think you can even buy them on Amazon as well. Or you can even use just mixing. So you can just put the stuff into a blender, shear it up, and that creates enough energy as well to kind of break them apart. So it's such a simple process because all of it just implies putting this in a liquid and then pressing a button and then waiting a couple of hours. And I think that's, as you said, like that's kind of the beauty of it all, is that like anyone could do this. And I think this is what leads to it being so easily applied elsewhere, is that you don't need this special expertise and you don't need these special instruments. As says, you can use a kitchen blender to make graphene. We've done a little paper on it. Jonathan Coleman had done a paper on it as well. And loads of other people have demonstrated. You can just get a Kenwood blender and just stick it all together, or just use fairy liquid and tap water, and then boom, you can make graphene yourself at home. So I think like yeah, you have summarized it well. And I think for us and for me as well, is that like I think it's that like, principle of kind of doing no harm, is that you can't like make a device or make a material that says it's going to help, it's going to help us as a society. But then in turn, when you make it, it's actually going to damage our health, essentially.
Yeah.
Is that you can't use like all these like mad solvents and everything because they have to go somewhere. And then who's that going to affect? It's going to affect the environment. It's going to affect our wildlife, the plants, us, our soils, everything. We're going to be poisoning ourselves. And I think that, like, I really kind of just had that kind of culmination years ago, or that's kind of idea instilled when we had a paper come out in Science, which is like, the holy grail of kind of
Yeah.
publishing. But it was called G putty. It's putty, it's graphene putty. So it was Play-Doh, or kids silly putty stuff that we put graphene into that I made in the lab. But what did it require? It required NMP, which is a toxic industrial solvent used to strip metals and polymers. Use chloroform, which everyone can know that is completely toxic. And then we use like IPA, not so bad. It's a rubbing alcohol, but we use like this plethora of solvents to make this material. And it just, after a while, I actually hated that paper because the fact is that we made this material that's supposed to be this health sensor that was supposed to maybe potentially kind of leapfrog into industry and kind of help people have a different scope or a different idea of how to make these types of kind of nanomaterial sensors. But I was just like, but we use all this terrible crap to make it. So you're essentially
Hmm.
making a sensor that's then going to inadvertently make you sick because of the processes and the industrial processes that would be required to make it. And that was kind of the turning point for me. That was just like, it's so counterintuitive and it's so disingenuous to be like, I make health sensors, and by the way, I make them in a way that's going to kill me in the lab, essentially. So it's just
I
like,
make them in the most unhealthy way
yeah,
possible.
yeah, it's essentially that. It's just like this is going to like absolutely tell you everything about your health, and at the same time could possibly leach into your skin and then make that health so much worse. So you might need to
Right.
buy more of the sensors. But
Yeah,
yeah,
yeah, yeah.
that's where kind of like it started to kind of settle into that. I was just there like I'd rather do something like that is kind of that's going to do no harm than yeah like just do any research at all. I think also kind of like we are talking before about kind of like being parents and kids and stuff, and I think that really kind of like becoming like a parent kind of really kind of settled in as well, that it's just like I don't want to kind of contribute to this kind of poisoning of the earth and then leave it to my kids to be like, well, sorry about that. It's just like I'd rather at least have some type of small effect, or know that I wasn't someone that kind of contributed. And I mean, like, I don't know, hopefully, like other people that do similar research might kind of buy into this kind of idea of, let's stop using solvents. Let's start trying to holistically think about how we kind of make our devices. I would love that. And then, like, I think, as I said before, is that like I'm under no illusion that like my research may or may not kind of have large effects in industry and the technology. But if that was the one effect that I had on other researchers of just let's really take sustainability seriously, I think I would say that that's kind of like a career accomplishment, even though I've only just started my career. If that's the one takeaway that people took from it, I think that that was great.
Hmm.
Yeah, it was just the whole idea of our research was this whole kind of just this economical, feasible, like how could you feasibly do this way of kind of using and applying nanomaterials on Mars? And we thought, what better way than having something that was already on Mars, that was using resources on Mars to be able to kind of, help these potential or help this kind of potential society. But I mean, it's certainly not kind of like the only way that I envision nanomaterials kind of, affecting space travel. Because I mean, I don't know, people may poo-poo kind of, the research that we had done, but there's other kind of ways in which nanomaterials can help, which is just the simple things of incorporating into the hulls of spacecrafts or into the suits of astronauts. Is that their graphene, for example, is really really good at reflecting electromechanical or electromagnetism and all this kind of stuff, and radio waves and radiation and all this kind of stuff. So it'd be very good at shielding, increasing the properties and the mechanical stiffnesses and heat resistances of all these materials. So I think like there's really kind of, I can see nanomaterials really kind of affecting space travel in some way 100%. Whether it's going to be our way, I would love it, but like who knows. But I mean, nonetheless, I thought it was kind of an interesting study, and I think it was just kind of an interesting case study for people of just being like, let's think about this economically and let's not mess up another planet, please.
Yeah, and that's what I really liked about it, because I had written some things before about green chemistry, about the movement of green chemistry, which is now probably like 20, 30 years old. Sort of this idea that the way that we make things in chemistry, chemicals, and all of these different things, they were back when we invented these processes. We didn't care about all the toxic materials that were required to make these things. Didn't think about it, didn't care, all of those things. And now there's like this new way of thinking, a new challenge of like, well, let's make those same things or even better things without using all of this horrible stuff.
Yeah,
And that's as you described, there's a moral reason for doing that, not destroying the planet and all that. But when you do that, when you view things in that way, you actually unlock a lot of other possibilities. And this Mars study that we've kind of alluded to here is, you guys really said, okay, well, we have gypsum, which is potentially a boring rock, but let's see if we can make nanomaterials out of it, nanotubes, I believe, in a way, like, again, put these constraints on for environmental reasons, but also hypothetically, what could a Mars, like an early Mars base colony kind of thing, what might they have where they could produce this material on Mars that they could then use? And it was like, what, like, you need water,
yeah.
gypsum's already there on Mars, you need water, and you need, I don't know, you could tell me the ingredients, but
Essentially, what the gypsum could be used from is that NASA had a study where they were taking gypsum. Gypsum contains or absorbs a lot of water and holds a lot of water. And they were just proposing that essentially you take the gypsum from Mars, you would then dehydrate it, you take the water out, and you're kind of left with like junk, essentially stuff that can kind of be thrown away or doesn't really have any use. And it's called anhydrite, so hence the name is just a dehydrated form of the original material, gypsum. But what we found is that you could take the anhydrite materials and you can kind of break them apart into these kind of nanorods and these kind of nano tubular shapes, and you could then use them into kind of plastics. You could put them into networks, electrochemical electrodes, to produce hydrogen gas, so clean fuel on Mars. And then you could also then use them as like, simple electronic materials. Essentially, they were like a surge protector, is that they would they could protect electronics and stuff like that from, power outages and stuff, sudden power outages. But yeah, we use these restraints of, taking this raw material, and you could then mix it in water to be able to make these nanorods. And the thing is that you're already making water from the dehydration process, so essentially you already have the water there. So that's already kind of two of the things done. All you need is some type of blender. I'm sure they're going to eat on Mars, so I mean they would have some type of kind of mixing instrument. I know that they do use so we call them sonic probes. This is the thing I was saying about the sonication of breaking apart nanomaterials. They're also called like homogenizers, as kind of, I guess,
mhm.
an industrial term. And they're used a lot in kind of generic experiments for mixing, and also kind of some biology experiments I know as well. And I know that that's something that they're interested in on Mars, of kind of like you're going to be growing plants, you're going to then need to be able to assess the quality of life of the plants, and you would actually use a homogenizer to kind of break up bits of the plant to be able to kind of like,
To break up the tissue. Yeah,
yeah,
yeah.
to kind of then examine it under microscope. So they would already have like kind of these homogenizers or these mixers there to then take this water that they just made and this junk that they just made and mix them together essentially to then make these a solution of these nanorods. And the thing is as well is that these aren't kind of toxic materials. The gypsum's used in food products back here on Earth, kind of ground up and put in as a kind of an additive, I think, for kind of calcium because they're made from they have a high amount of calcium into them, so it's kind of like supplementary kind of food. So I mean, like you could technically have astronauts eat some of the anhydride stuff as well. I mean, like I know that there are issues with kind of bone density and stuff in space and space
Because of
travel
the gravity, right?
because
Yeah.
of the gravity and stuff. So I mean, like I don't know if then them being able to kind of eat the gypsum or eat the anhydride will actually be beneficial to their bones once they arrive to on Mars, that they need like this sudden influx of loads of calcium to help kind of reinforce the density of their bones. And but yeah, essentially we kind of took this whole idea of just like they already have this stuff on Mars. So it's just like in tangent or in parallel, you'd be able to kind of make these kind of very useful materials. And I suppose one of the things, like I suppose restraints was like I think kind of the word that we had used in kind of the paper, and always kind of something that I thought of initially when we were doing the work. But I feel like now, kind of like retrospectively looking back, is I feel like it wasn't really like it's not really like a restraint to use more economical, more environmentally safe materials because there's so much of it out there. So it's not really. It's more so just looking elsewhere rather than kind of just being like, oh, we absolutely cannot use these materials. And you kind of think of another way of just like there's all this other stuff that we can use instead. It kind of
Right.
it seems less kind of daunting than that. It's just yeah. Looking back, I feel like more positive about it. Whereas before, I was just like, oh no, we can't use a solvent here. How the hell are we going to get around this? And like, could they use that up there then? No, they wouldn't be able. Like, they wouldn't have IPA up there possibly. I guess maybe they might have it for rubbing alcohol if they had wounds, but maybe they wouldn't want to use it or it wouldn't be in a way that we would be able to process it. So it's just like at the time it did seem like restraints, but now looking back, yeah, it just seems like it's just no, there are loads of options there. I think it's just changing that frame of mind of just being like there are other ways of doing it. It's just I've been taught to only kind of do it one way, and I think it's kind of just trying to move past it. And at the moment with our other research as well, is that we've before we're like you can't make good sensors or for wearable sensors out of anything but like silicone and all these kind of really stretchable industry available materials. And we're just like no, there must be other biological materials that are out there that are ready for the taking. And we found seaweed as the kind of the ultimate kind of material that we found that's really really good at making sensors that a lot of people just kind of just I suppose they probably just don't investigate because just everyone does polysilicon and solvents and all this kind of stuff. So it's just people just need to change the mentality all around.
Yeah. I mean, I love that not looking at it as constraints, but rather, well, look at all of these other materials that are available, right? Like just
Yeah.
flipping that positive negative kind of thing. But it's kind of cool to me that it takes, limiting yourself or saying I'm not going to do things in the way that we've always done them, which again feels like you're giving yourself boundaries, you're giving yourself, this box that you have to operate in. But in doing that, you just on the other side of that box, you open up this wide open space of all the stuff that is available, which is,
Yeah.
I don't know, like just, I don't know, it's just a neat
I
sort of
think it's just like
philosophy sort of thing.
thinking about it, it's just like before I now think like I had my blinkers on then. I was restraining myself then because I was just like, this is what everyone does and this is how you do it. And I
Yeah.
now feel like that's more of a restraint. It's like you need to be more flexible. You need to you need to think of something else.
Yeah. Yeah. And then just investigating the things around you. So the seaweed then, what is it about seaweed that you found and how did you cue into seaweed? What gave you the idea for seaweed?
Seaweed came from lockdown and watching MasterChef. I got the basically it was they made these things called like food caviar. So it's like they get like pureed prawns or jams or jellies and stuff, and they just mix it with the seaweed polymer, and then you then drop it into a little bath of salts, calcium chloride salt, which is also edible as well. And it would form these little capsules where you'd have the jam in the middle, and then you'd have like a hydrogel layer surrounding it. So you could like pick it up and hold and stuff. You might have seen it kind of like in like fancy restaurants will try and like I don't know, put it across as like, ooh, fine dining experience, but it's just literally you're just kind of eating goo. But yeah, I just kind of just had this idea that I was just, that seems really interesting, very firm, very pliable. I was like, well, what happens if we put graphene into it? And that's really where it kind of just spawned from, is that we put graphene into it and just found out that like just the system of the capsule itself was just such a cool system that we were able to kind of control so many parameters about the sensors that you can't do with any other material. And it just allowed us to get just a really fine understanding of just generally how nanocomposite, which is nanomaterials mixed into a polymer, how those systems work in general. So, like globally, we through this stupid idea of watching MasterChef, we're now able to kind of predictively understand and predict the performances of nanocomposites, not only our own, but other people's sensing materials, just using our modeling just from MasterChef. But it just like it's just it was just like it's just something that was just the fact that it was like a sensor that you could eat. I was like that. There's nothing more kind of economical and environmentally safe than that. It's like if you could eat it, and fish eat seaweed and stuff, and the wildlife can metabolize. And I'm just like, this is then like a win-win. It's something that benefits us, but it's not hurting you know anyone else.
Yeah, and then you got to think too, like the cost of the starting material. Like if
Yeah.
seaweed is a basic, that's you could grow a lot of seaweed. I would imagine pretty cheaply.
It was,
Uh,
yeah,
you know,
it's very, very cheap starting materials, and it doesn't like use a lot of the material that we bought. Granted, we got completely screwed because the first time I bought it, I went to like this fancy gastronomy supplier and stuff, and I bought the seaweed from them. It was really expensive, and then I then bought the same seaweed off Amazon. It was literally exactly the same thing. And it was like, I think the first time was like £50, and then the next time was like £5, and I think we got double the amount off Amazon as well. Oh, I felt like such an idiot, but I was just there like I have to get stuff that they got off MasterChef because that might be the only stuff
right.
that works. Oh yeah, we felt like such. Well, I felt like such an idiot, but we got there in the end. But yeah, it was a very unnecessary expense on my behalf.
That's great. All right. Well, we could wind things down here. We've been talking for over an hour now. But I think that's to me I love this idea, like you said, of this philosophy of like do no harm, and it really shows. And like I said, I never thought I would be covering this kind of stuff when I was an undergrad because I was so bad at chemistry and all this. But I really think it's such a fascinating thing because we talk, sustainability, the environment, it is a big thing in the world right now. Like everybody's talking about it. And it feels at times that it's like there's not a lot of progress being made. But I think what you're showing is that there's a potential way to do things. And it's less about we don't have the technology to do it, but it's more about we're not looking in the right places or we're not
Yeah.
thinking about it in the right way, which I think is a very inspiring message. Now, do you think this might be less inspiring? Maybe I'm gonna turn it here, but we have all of these interesting things, like this way of thinking, the things you're talking about doing. Other things I've heard from similar people doing this type of research is that there is this inertia to get the uptake of this kind of thinking, this kind of technology, that kind of thing, because systems have been built, the economy has been built on doing things with hydrocarbons, with oil, with petroleum, all of this stuff. So it's going to take this time to convince people, but then also actually to like physically, dismantle you have all these big petrochemical
Yeah.
plants, and it's like for a company that's like, okay, I like your product, I see that it's beneficial, but I've invested millions of dollars in this factory that does it this way. So I'm not just going to abandon that now. Do you
Yeah.
see that as a challenge to overcome?
Definitely. I mean, it's historically, it's happened loads, even with like the electric car. Because wasn't it? I can't remember what supplier it was, but I think it was an American kind of manufacturer. Is that there was the idea of the electric car and the ability to do it, but they kind of poo-pooed it and kind of shelved it, just being like, we're not doing this because, yeah, as you said, we're invested in making cars a particular way, and they're selling, and why would we then disrupt the market? So it's just like, yeah, there is that kind of impedance because, like, I hate to say it, is that, like, yeah, some nanomaterials are not as economical as others. So, like, I'd say graphene is quite economical because, it can be naturally sourced. Like, you can find graphene, but there's other materials that, like, you can get large, very large pushbacks on, like, things called maxines. So they're kind of titanium carbide materials, and they require a lot of harsh conditions and harsh solvents to be able to kind of just make the materials at all. But they're one of the largest and most investigated materials in nanoscience. And like I'll admit is that like I've had large pushback from reviewers and editors like having to have sentences removed from publications naming them as potentially a pitfall in kind of research is that yes, they're a material that's very highly investigated, has fantastic properties, but if we cannot make them economically and environmentally sound, then maybe we shouldn't be looking at them at all. And yeah,
Hmm.
I've experienced slight pushback with certain kind of statements like that is that some nanomaterials just shouldn't be investigated because yeah, like you just can't make them. Like I think like I can't remember specifically. I think it's like Maxine's just to make the briquette thing that you get the nanosheets from. I think you have to put it in an oven at like 1200 degrees, some materials and these harsh gases and kind of these rare elements and it takes a really, really long time in the furnace. And then when you get them, you have to use like hydrofluoric acid to etch the layers out. So like stuff that like they had in Breaking Bad, like dissolving bodies
Yeah.
and stuff. So it's just like really kind of like dodgy stuff. And it's just I understand that they have fantastic properties, but it's just one of those things. Where's all this waste gonna go? Like if we're gonna go, okay, Maxines are the way forward, and this is what we're gonna be using all the time. It's just they're like where's all this junk gonna go? Like it's just yeah, I have seen kind of small pushbacks with regards to that, and not so much kind of I suppose like things like seaweed and kind of like alternative polymers and stuff. I have to admit that people have been kind of quite receptive, and I do see people like the trends are kind of going up that people are interested in those types of kind of materials. I don't know whether now it's kind of because it's new and it's sexy and it's kind of something's interesting and might be more impacting, might get you into a better journal. I'm not really sure. It's kind of hard to say. I'm sure it's probably 50-50 of people consciously wanting to do better than also thinking jackpot, this is going to be a really good paper. But I'd like to kind of give people the benefit of the doubt and think that like people really do want to kind of make these changes. But yeah, I think the only kind of pushbacks that I personally have ever experienced was kind of I don't want to say naming and shaming certain materials, but just kind of just saying like we have to ourselves as researchers just say, we set this benchmark. You need to be like at this level of environmental sustainability, and if you don't meet it, maybe we shouldn't be looking at this material. We shouldn't be funding it, and we shouldn't be investigating it. But I mean, I know those are probably like big statements anyway. But I mean, like it's probably never going to happen because yeah, vaccines are just as I said, they're the biggest ones that I think are kind of the biggest issue because there's such huge investigation into them, but they're just so terrible, it seems, for the environment. Despite I think what I don't know people say, and I mean they've changed the way in which they synthesize them, but they still use harsh, terrible solvents because it still has this issue of that the maxines are kind of like graphite is that there are layered materials, but with graphite it's van der Waals, so it's these weak intermolecular forces that hold the layers together. But with
Right.
maxines, it's covalent bonds, so there's physical an atomic layer that holds them together. So you have to etch away those atoms to be able to separate out the sheets, and you have to use harsh solvents to preferentially remove those atoms to get the layers and get these kind of nanosheets. And there's no way around it. It's just you always have to use these harsh acids. You always have to then use these harsh bases to then quench your solutions as well, to be able to, kind of remove or reduce the acidity to be able to process them. And yeah, I think it's it's one of the biggest issues. I think is that, as you said, it's that people have invested so much in kind of certain things. It's really hard to then reel yourself back in and go and maybe take a step back and go like, is this the best idea? Like, and I don't blame people. As I said, like, the Maxine stuff, they have fantastic properties. They really, really do. And they've had fantastic studies on their abilities and being able to kind of perform in large area, from energy to, computing to even wearable sensors as well. But it's just, yeah, it's very difficult to then take that step back and go, okay, I'm going to completely change essentially field or kind of do a complete pivot and go to something else. Because I mean, it's a gold mine. Like, the journals love the Maximes because they have so many interesting studies that come out on them.
Hmm. Yeah, I think this is where, and it's not completely my idea. I've talked with other researchers about this kind of stuff, but it's like this is almost where you need, um, there, those kind of costs are not, the environmental costs are usually not, built into the economic model of, is this going to be profitable or not? And this is where,
Yeah,
things like politics, policy, laws that put a penalty on that kind of thing, So we were talking about putting constraints on and maybe not looking at it as constraints, but this is the analogy I'm going to
this
use,
is
is like putting constraints on, or a cost on that kind of thing, right? Seems like a way that we could push this further, push the
yeah,
sustainability thing further. Because what I hear from researchers all the time, and kind of I think what you're saying as well, is like, it's not that we can't do it. There's all of these other options out there. There's all of these other materials out there that we can use that will be, better for the environment, better for all the things, and they would still do the things that we want them to do, and we could do it in an economic way. Like, it wouldn't challenge the cost that much, but there's just this momentum that needs to build up, and you got to make the case, and again, I think pricing environmental damage, is a big part
yeah,
of it. But
and
that's
it's hard to
probably a
quantify.
yeah,
Um,
that's a whole nother challenge and a whole nother podcast for another day. So
yeah,
let's we can end it there, because I think it's still a positive note. I don't think that was a negative note to end things on. But thank you so much for taking the time. I really enjoyed the conversation. It was yeah, really interesting, and I'm going to be following this stuff again. I'm going to continue to follow this stuff, is what I mean to say. And you're welcome to come back anytime
oh
to
yeah,
talk about more seaweed updates or space, or whatever
hey,
wherever the nanomaterials bring us.
hey, there's a lot of things they're going to talk about in academia that, people just, I don't know, they just kind of sweep under the rug. It's a weird I don't want to say industry, but yeah, it's a weird work environment and stuff. It's tough. As an early career academic, I definitely kind of sympathize with people in similar positions. It's taxing. It's definitely kind of taxing on kind of mental health and stuff. And I think that's kind of one of the yeah, I don't want to now end on a bad note or whatever, but yeah, I think that's also kind of like one things that I would just love people to talk about more in academia. I think it's kind of just mental health. I think it's a very, very important kind of topic that kind of gets swept under because I just think it's a very different industry to, working in a company or anything like that. It's so lax, there's no real like line managers and stuff, and you have multiple people to report to, but then also you're then, if you're a PhD, you're working on your own project you know that you're kind of self-starting yourself. So it's just, yeah, there's a lot of kind of moving parts. I think that's kind of the main takeaway. Look after yourselves, essentially. Yeah,
Yeah.
it's a tough industry.
Yeah. I mean, there's pros and cons to it, right? Like, it's, the freedom, this thing we were talking about, you're getting to pursue this ultimate curiosity kind of thing, being sort of at the creation of new knowledge, all of that stuff. But yeah, the sort of work environment and structures in place for that, all that kind of stuff is, I think, yeah, it needs to be examined as well. I think
Yeah,
anyone that's gone through academia that's listening to this will be like, yep,
yeah,
I
it's
could feel
yeah.
that. But yeah, maybe that's again a topic for another show.
Part
So
two.
thank yeah, part two. Yeah. Thanks again so much for doing this. I really appreciate it.
No worries at all.